Yeah, today I would like to talk about the data lake implementation, about the project that I was actually participating as an architect at EPAM. It's also about the architecture based on the multi-tenancy and developed on top of the AWS Cloud. So a few words about me. I'm Alexey. I'm working as a data architect at EPAM. I also like functional programming and music. You wanted to contact me, you can also use my blog at this address at GitHub.io, where I post time by time some articles. This project is based on the real experience working at EPAM. One of the clients who is a leader in stock management software, so they have a software as a service platform where we, EPAM team, were developing for them and still developing for them the data lake or / data platform. So what we're going to cover today, it's several blocks in our agenda. So we'll go through the main architecture diagrams. There's going to be a separate block about multi-tenancy. We'll also look at the standard workflows that we've developed for this data lake story, main use case, and how we've done that by building this data lake, what practices was used, specifically continuous integration and deployment, and several improvements that we identified while building the platform, and we're going to address them in future. So in a nutshell, if we look at the data lake as a main component of the data platform, it may be, it can be expressed at this as on this picture. So we have something in the middle as a data lake, some kind of compute and storage, abstract computing storage, where we aggregate data. And we take this data from some products, some transactional data, so-called LTP data sources, and we bring them to the lab world. So those two words, I believe, are known to those who are working in data space. And we are aggregating this data in data lake and provide this data for business intelligence in terms of the reporting. We also use this data for data science experiments, for machine learning, and simply just to export the data in more convenient format, maybe to give it to the client, a team, or somebody else in the company. While developing the data lake, so I must say that while this presentation, I will use data lake, data platform as synonymous, because for this client, this was more or less equal things. But I think we all know the data platform is something bigger than data lake. It may encapsulate data lake, but may have much more components. So for this particular story, for this particular client, while building the data lake or data platform, we found that we can easily underline or have a borders between components and identify which components we have actually at the very beginning. So, and yeah, on this diagram, you can see those components as well as the names of Amazon services that we used to build this component. So we don't really care about that much which components we change or modify. We more driven by business, but from the engineering perspective, it's important to know like which component is working with each other or what changes we do where. So for queries, for query engine side, we use Apache Spark, Athena, and Redshift Spectrum. We also have some APIs which we develop within the Amazon Lambdas together with the combination of the API gateway. In order to orchestrate our pipelines, we use Apache Airflow in terms of the MWA service that Amazon has. So this is to manage Apache Airflow. For metadata, we use Glue Catalog. For data integration and data transformation, we use DMS for the integration, and again, Apache Spark for transformation. Classic storage for the data lakes in Amazon S3. And configuration, we also use S3, objects or files, and some configurations also kept in the DynamoDB. And across all layers, across all these components, we use Amazon IAM, and everything is controlled by IAM roles and policies. And also important to say that while developing all this platform more than 1 year, during the year and more, we were as one of the team who were also maintaining this platform. So there's no separate team who is changing this from the web perspective or who is promoting some changes to the same team, platform team, operating all of these components, providing the policies, developing new features and new use cases on top. This client is quite interesting because it has more or less global scale, and it represents itself in 3 regions of Amazon. So you can see here that one of the region is US 1, then we also have EU West 1, AP Northeast. So this is the North America, right? The US 1, Ireland, Europe, and AP Northeast, Tokyo, Asian region. So this is about complexity of the deployment. So we have 3 regions, and also we have separate accounts. So if we calculate that, how complex our deployment and how many targets we have, it's basically 3 multiplied by 3. We have 3 environments to maintain, to deploy. We don't have some connections between these environments, like from production to development. That's also a policy there. And from the switch perspective, when we working on some of the environments, so basically, if you are a developer, most of the time you're working on this environment, then there is a specific account, right? So there are 3 accounts with 3 regions. That is why it's 9 environments. So if you're working in the development account, and you can switch between different regions in order to test your deployment. But actually, all deployments are the same. The only configuration is different, and different data sets are deployed in different regions. Now let's start with the main diagrams. So the main data flow can be represented as following. We have some components that we group together, and we call them as data management layer, where those services to aggregate data, to integrate data, to orchestrate the pipelines, to store this data, and add some metadata to our platform. Also, we have query engines to query this data. And of course, we can't live without the security, so we have IAM service everywhere in this layer, right? I already mentioned which services we used in the components right before. They are all listed on the left-hand side. And if we also look on this diagram from a data flow perspective, right, from where the data starts and move to where, what's the destination. So we have those data sources, like today they are mainly RDS instances, Postgres databases. This is the current use cases, but there could be also future use cases where the data may come directly from some S3 bucket which is maintained by somebody else, by another team who's sharing data to us to be aggregated into data lake, or some kind of message queue. So once data is integrated or extracted from the data sources by DMS or maybe by Spark directly, it's stored in the S3. We also registered into the Glue catalog. All of this compute tasks or pipelines are orchestrated by Airflow, MWAA, right? So the managed workflow for Apache Airflow. And eventually this data available can be queried by Athena or Redshift from those users who are using some BI dashboards or some client applications, or some consumers who are working for data science services. There's also an interesting layer or component that we've got while building the data lake, which kind of sits on top of this compute and storage components, the API layer. So it's more or less programmatic access for different things. Today, there are 2 APIs that we provide for other teams to call some of the workflows externally. So how does it look like from the Amazon architecture perspective? So which services we use? I already mentioned this. The main code is deployed as Amazon Lambda, and there are 2 of them today. One of them is called Workflows API and the Custom Columns API. So yes, you see that they are behind of API gateway with specific authorizer based on the IAM role. Also has static DNS record or just DNS record that can be used by other teams or clients to query this API. This API also, for example, if we talk about the workflows API, shortly, it allows to trigger some of the workflow from Airflow perspective externally, and custom columns API allows users to customize the SQL views by writing SQL expressions, and these SQL expressions will be used to generate a SQL view at the very end. And the SQL view will be or can be used by any consumers, and the main target use case is the business intelligence tool that can query the data through this SQL view. So basically, that's the way to customize the final shape of the table that the BI will be using. That's two APIs that were developed for the main use cases, but there, of course, we have in mind the future APIs. So we have some to-dos APIs, like provide the status and health of specific data sets, and they encapsulated in terms of the tenant, which I will uncover later in this presentation. And also to provide some kind of API to add new tenant to the system and or remove it from the system. Let's talk now about the multi-tenancy. So multi-tenancy is one of the main requirements for this customer. So as I mentioned, this is the software as a service company, and they provide this software to other big companies who maintain lots of data about the inventory or stock, some items in the warehouse, and this data can be also used by these customers who are using this whole platform. So the whole platform is much bigger than our own piece, which is data platform or data lake. So this is drawn here as this bigger box SaaS platform. And from our team perspective, so we are a data engineering team who's operating piece of the data lake infrastructure for some of the tenants. So the data lake itself or data platform within the SaaS platform is a multi-tenancy platform. So here we can see that there is some tenant A. It has its own data plus compute resources. And all of this implicitly belongs to some customer, to some company who has made a contract between themselves with this SaaS company. And for us, for data engineering team, means that we need to onboard this tenant to the platform, to the data lake platform, and create something for this customer, either in advance or maybe then lazily when it comes to run the first time this pipeline for this tenant. So there could be, of course, multiple tenants, and they all have the same set of static resources, but the dynamic resources like data sets, or tables, or data volumes that, of course, different per each tenant. What are the requirements for tenancy or multi-tenancy we've got? So they are quite common ones. So we need to isolate tenants' data in terms of the access and security. So we cannot allow users from one tenant to access data of another tenant. So from business perspective, this is one company who doesn't even know that it's also using this infrastructure as another company, or maybe there could be even some competitors. So this, of course, must not be possible to access any other data than your data as your company. And computer isolation. So we provide this software as a service, and there shouldn't be this problem of so-called busy neighbor, where you are running your stack on with some other companies. They should not have this performance issues where they running some heavy loads and affect some other customers. So we need to guarantee that as well. So what we've come up with is some stacks of resources, which we are called account resources, common resources, and tenant resources. That's all these layers enabled us, or design of this enabled us to then focus on this, what is actually the tenant-specific resources. So here, resources, I mean, all what we create in the Amazon inside of these services, like S3 buckets or IAM roles, or tasks within DMS, or glue jobs, all what you can imagine, all these tasks, all the footprints within the Amazon. It also corresponds to resources in terminology of the Terraform tool. You might know this DevOps tool like Terraform. And it also has all this unit of the configuration called resource. So that's coming from that word as well, but it's kind of mapped to Amazon things which you create programmatically as well. So what we have schematically is, if we look at these layers, they are based on each other, right? So the main basement or baseline is the account resources. The Amazon account gets resources which are shared across regions. And then within each region, we deploy common resources. And on top of the common resources, we deploy specific tenant resources. There could be from 0 to n tenants in a specific region. That means also that account and common resources are shared to the specific tenant resources. We will look at in a second what exactly is shared and what is not shared from a tenant's perspective. So that's another view of the tenant resources, where you can see actually what is shared and what is not. Let's compare this tenant A and tenant B views. So most of the things are specific, so isolated, right, from each other, like glue jobs, IAM roles, S3 buckets, different things like Athena work groups, DMS endpoints, tasks. This can be easily isolated, so they can be created per tenant. You don't need to really worry. Thanks most to that all of the services are like serverless. Yeah, all apart from these two which are shared one, like so these are Airflow cluster and Redshift cluster. So we use Airflow, as I mentioned, for orchestration of the data pipelines, and Redshift we use in specific cases for some of the clients who wants to query the data through Redshift specifically, or they have only interface with Redshift, so we provide this query engine. So Airflow, from Airflow perspective, the service which is today, it's not serverless, it's serviceful. So you provision specific cluster or specific in-situ instances, and then you run as many workflows as you need, and then you can scale this cluster, right? But in order to create these clusters to isolated per tenant, that would be quite costly. So that's reason for Airflow, actually also for Redshift, that we create a cluster per region, and then we share this cluster to all the tenants sitting within the same region. Then, of course, we make sure that tenants running within the same shared clusters are isolated in terms of the configuration and security access, so they cannot really read its own data, for example, from Redshift perspective. So in Redshift, there is you can have many databases in one cluster, many schemas in one database. So all is controlled by the permissions within the Redshift itself. From the Airflow perspective, it is a bit loose security configuration, but since it's the main tool used by the data engineering team, there is no need so much for isolation between the different DAGs or workflows within the Airflow cluster. Also, it was worth to mention that some of the resources are created lazily. Like if we onboard new tenant to the system, we don't create everything at the very beginning. Of course, there's some static provisioning of the resources to some specific region for a tenant, but then when the first time we run some pipelines for a specific tenant, they create additional things like Glue databases, Glue ETL jobs, different DMS entities that it requires, or AMR cluster, for example. For some of the cases, we, instead of the Glue ETL, we use EMR to run Spark jobs. From configuration layer perspective, how the tenancy affects this layer. So let's look at this diagram as well. So configuration layer is there are two pieces. First piece is this Terraform scripts that we maintain as a data engineering team. The scripts defines all the structure that we need to create in Amazon. And what it does, it first of all creates this all native resources in Amazon. Also, it uploads a couple of business configuration to our space, right? To S3 buckets, special S3 bucket, and to also a special, we call it system resources, some data to DynamoDB as well. And eventually, our configuration is used by Spark jobs, right? So we read this just simply from S3, from AMR or glue job. Also read some system configuration by the Airflow itself when some specific DAG or workflow is running. Okay, so that was block about the multi-tenancy. Let's look now on the standard workflows, which we have developed while satisfying most of the use cases for this customer, building the data lake for them. So in order to pull the data into the data lake, you have to have perhaps one or two standard pipelines, which we call them as initial load and incremental load. And so the first day you start some kind of data lake, you need to load all the data that you already have in the organization, right? We also have here multi-tenancy, right? So that means we in data lake, we slowly onboard different tenants, different sub-clients of this client to our world. So we don't need to load all the tenants at once. So that is why all the workflows, all the things, they are tenant aware. So from initial load perspective, we have some client that wants to be onboarded to the data lake, and we just run it manually on demand, this pipeline, and we upload the whole data sets, all the tables for this client for specific product to the data lake. And that's it. So we stop this pipeline. We don't run it ideally anymore. And then incremental load starts right after we finish with the initial loads. It runs 24/7, and it just loads the delta to the system. Also, we have like main pipelines for aggregation or data transformation. We call this pipelines derived table builds, and auxiliary pipelines are from category of housekeeping. So derived table build is some kind of different business scale queries, which using already data which is already in data lake, aggregating it, processing it, and creating special shape for these data sets to be consumed further by BI tools, for example. And housekeeping are those special auxiliary jobs which are only needed and maintained by the data engineering team, and they are optimizing storage, mainly the deleting all data. So you got to have this type of jobs anyway in the production system to maintain it over the time. Now let's look in detail. So how we've built the initial load from the workflow perspective, and also how the steps are mapped to the Amazon services. So we'll go through all four types of the workflows we have. So what we have here is the two Airflow DAGs. And the first part, the first DAG for initial load, it just spin up the DMS task. And this DMS task is doing actually the main work at loading data from database, from RDS database to S3 in Parquet format. So this DAG is running on its own, and it's implicitly connected to the next DAG, but they are like not aware about each other. They're just shown on this diagram that they make sense. They are part of the same picture, or the bigger picture. And the second DAG is taking the uploaded data and registering it in the data catalog, and also optionally can already prepare the derived table. So can already prepare some aggregates for the future use by the BI tools, for example. I probably also need to say that we use some technologies here like Delta Lake, which I'll uncover in a separate block also during the presentation, which is we take the data and register in the data lake tables. So that's also important thing to keep in mind. Incremental load is very similar to the initial load. So if I go back, right, so to initial load and then again to incremental load, you see the pictures are very similar. The only difference is that incremental load this time starts ongoing and continuous task in DMS here, and the DAX is just triggering that, and DMS is running the task 24/7. And this delta or data are also stored in the S3 bucket as raw data in Parquet format. And time by time, we run this job to increment deltas to ingest the deltas to our main tables. Yeah, also probably worth to say that one of the main feature that we have here in incremental load, or the approach that we followed, is that we already have some data in data lake, right? So we have these deltas that is coming constantly to our system. So in order to synchronize the new data with the existing data, we need to merge this data with existing one. So usually it means so-called upsort or insert if it's missing, or update if it's there already in the target, or delete if the data which is coming to us with the flag delete. That means we need also delete in our system. Also, over the time, we developed another version of the incremental load using Spark streaming. So I mentioned that on the first version here, it's a batch approach, actually. So here we run DMS continuously. It's giving us the deltas. But further, in order to ingest the data for consumers to read this data, we have to either configure the schedule for this DAG to ingest data to the data lake, or trigger that manually. So next version, evolution of this incremental load pipeline, is to split the second part into two parts. So now we have kind of 3 DAGs for this global picture, or bigger picture of the incremental load pipe workflow. And the next version of the incremental load for the Spark side looks like this. So we first we change the ingestion from batch to streaming job. So we constantly pulling the files from S3 and merging them to the data lake table. That's just a standard feature of Spark here used. And then we extracted the part where we built derived table, which needs to be triggered still on a schedule or on demand by users in order to create new aggregate, a new BI report when they really know that, okay, the data probably already came there and they need to new version by next morning, for example. So second part is not really feasible to do in the streaming mode because of so very complex queries that we have. So basically, it's a graph of queries to be run in some specific order. But also, the nature of the data is not really in this kind of streaming way that you would need to have this real-time dashboard here. This is more or less summarizing what I already described. The first DAG is running a streaming job. The second DAG builds derived tables in a batch mode. Advantages of this approach compared to the previous version, that new data is available in the raw tables close to real time. Disadvantages are that you run the Spark job 24/7, so your Amazon cost or service cost is rising. So there are some options for mitigation, how to do this, how to minimize the cost, perhaps use EMR cluster and try to optimize some instances and maybe share this cluster for other workflow for the same tenant. So there are some already ideas how to minimize the cost. So yeah, that's a whole topic on its own, how to reduce the cost of the Spark jobs in Amazon or any other cloud provider. And housekeeping jobs are very similar. So there is just one Spark job running on demand. There's no need for streaming or jobs like running continuously. It's doing time by time, once a week or once a day, some compaction of that, or purging the old data from the data lake. All right, so we are now at the next block about workflow implementation. So how we develop them, how we program them. The main thing we used is Apache Airflow. So the quick facts or reminder about what is Airflow. It was developed by Airbnb, open source in 2016. It also available as several options right now in the market, and Amazon has its own managed version. important concept in the Airflow called DAG, directed acyclic graph. This is the abstraction that you express your workflow, and you express that only in Python, so only programmatically, which is very suitable for us. By Airflow, we orchestrate many services in Amazon, and I also highlighted them here in this diagram. What is actually those services and why do we orchestrate them? So in order to do data ingestion, data aggregation, we use these services or orchestrate these services by Airflow, like EMR, GlueTL, DMS, and Lambda. And we also read some configuration by the workflows, by the DAGs from Airflow, from the S3 and DynamoDB. There was huge work done to support multi-tenancy in Airflow as well. So as you remember, Airflow is shared cluster for this architecture, and in order to have multiple tenants running within the one Airflow cluster, we come up with some naming convention for the DAGs. So DAGs are those workflows which have unique IDs, and you can see them on the pre-spring screen where we have some convention. I will uncover that on the next slide. And that's a requirement from Airflow perspective itself. So we cannot have two DAGs, two workflows with the same name, so that doesn't make sense. The convention is quite simple. So we have some encoded tenant name plus the DAG name. So we call it DAG type. For some workflows or DAGs which are use case based, kind of, we also have additional differentiator in the name, which is we call use case name. So you can see here that the tenant name is price datalake QA. So this is the experimental tenant name. So it doesn't really make sense that much from the business perspective, but this is like transparent ID, the whole name. Then we have use case name called sales history and DAG type, derived Spark. That means that this DAG will be built in derived table and it's based on Spark. In order to generate all these DAGs that you've seen on the one of the previous screen here, so this is there are 11 DAGs today per tenant. So every region may have maybe 20 tenants. So we will have more than 200 of DAGs within one cluster. And we don't want to copy paste the same DAG code to every tenant, right? So Airflow allows us programmatically also to generate DAGs. There is a specific import process in Airflow, and we've come up with some configuration in JSON format, which can be used, which we use to read it during the import time, and we generate programmatically the DAG. So basically, we have a couple of Python files which are programmatically generating hundreds of DAGs, and that's actually, it's not, so if you know the Airflow, it's not that we have many 200 files of Python or just one file, but it's just creating the objects in memory, which is then used by Airflow to create these DAGs in its own application. So this configuration shortly looks like this. We have an array of objects where every object is a tenant definition. It has some properties. It has some scheduling properties for types of the DAGs, and also for DAGs for use case-based DAGs. So these are the names of the DAGs, and there could be optional schedule, like cron-based schedule, or no schedule means somebody would trigger this DAG on demand. From code source perspective, this is the Airflow source code we have. There are different files. We have also structured these files per product. So this customer that we developed datalake for has specific product, about 6 to 8 products. One of them is called price. And for this product, we have specific code developed to have these pipelines. They aggregate a specific package, but there are not that much code per tenant. So all is quite generic. If we look at the DAGs that were developed by us and then rendered by Airflow, we can see that there are quite complex one for DMS pipeline orchestration. So in order to run something DMS, we made it very small steps to orchestrate all the things in DMS. This is the DAG for full load. This is the DAG for incremental load. This is only DMS part. You can see that the DMS CDC part or incremental load is much more complex. So it has lots of steps. So it's rather detailed ones, but if we compare with the Spark docs, they are quite simple one. The reason is that Spark job is the program that you trigger, right? And this program can be any complexity inside. And from Airflow perspective, we just have this command like Spark submit or just trigger this Spark job somewhere in the cluster. But from Airflow perspective, we have just one task. So this is the initial load DAG where we trigger 2 jobs like ingest data and derive tables. Incremental load similar, 2 steps to 2 Spark jobs. For streaming option, it just split it into 2 different DAGs. So a DAG with 1 task only. So they're much more simpler, but this is neither good or bad. So this is just how it went with regards to technologies like Spark, where you write also code on the side for your programs, and DMS, which is just a serverless API from Amazon, which you use in here to create such a rich workflows where you control every simple step here to create different configurations, start the task, wait for task, destroy task. So that's the reason. And for housekeeping jobs, similar. So they are also Spark-based, just 2 tasks and 2 separate DAGs. Okay, so now we're going to explore some key technology that we used to develop this data lake, and it's called Delta Lake. So Delta Lake, it's a library developed by Databricks, and it's open source project as well. It's part of the Linux Foundation. And this technology, in a nutshell, and compared to what we needed, provides the ACID transactions for data lake, upserts and deletes for Spark, schema evolution, the time traveling feature, so you can have different version of the data in the same table, and much more. Yeah, and it's also, I forgot to say this, it's a main target runtime for this library is a Spark, Apache Spark itself. So we're using this library within Spark jobs. And also, it worth to mention that the whole idea of the Delta Lake library is to enable so-called lakehouse architecture. So what is lakehouse architecture? You may find much more information on the Databricks website. They are basically found this name and terminology and the whole architecture and movement. But what they say is that we know what is data warehouse, right, and what is data lake, which can be represented in a way that in data warehouse you have some ETL process that extracts data and stores in its own storage, and then allows BI to consume this data. A data lake, we have 2 things, so like a data warehouse as well as the data lake itself, the files, the blob storage, where we use 2 things for different use cases, one for BI, one for data science, machine learning. Data lake, lake house, it's kind of a combination of 2 worlds where we have all the nice features of the data warehouse plus data lake itself, cheap storage, cheap compute resources, and all of the whole data lake plus specific technologies are now called Lakehouse with the data lake library, and that allows you to provide the data to all the type of the consumers. Before choosing data lake for our data lake story, for data lake implementation, we also compare that with Apache Hudi. So for somebody who's interested in the Apache Hudi, this is what we found as a strong and weak sides of Delta and Hudi. So both are fine. They could meet our requirements with regards to the transactions and merge operations. However, Delta showed better results and better performance, and also better quality in terms of the documentation and the runtime itself. So we've chosen Delta Lake, and we did a lot of tests in order to switch or just focus on Delta Lake itself. A bit of information on how to query, how to use Delta Lake in Amazon. So it's not natively supported, like, for example, in Azure. So in Amazon, you just do a simple trick. So you use that as a library within your Spark job. So you just need to have this library on your class path of the Spark job. So you can just in advance upload it somewhere, like to S3, and then use the path to the jar in your Spark job. in order to read the data from the Delta Lake table by Athena or Redshift, it's also one more trick. So there are so this is the main trick, and the trick for using the Delta Lake as a library, just standard approach how you use any library for Spark, right? So this is not really specifically to Delta, but this one is about to query this Delta Lake tables by services like Athena and Redshift by Amazon. There is official recommendation or workaround how to do that, and it's in a nutshell, we just need to create additional symlink table, which will reference the whole data via manifest file. And in order to do that, we just need to apply a few commands. They're also available from a SQL perspective in order to just link this data and then provide it to be queried by Athena and Redshift. So what's going on here? We create the manifest file with the generate command for this table and all the references to the Hive metastore or Lookatalog. And we create one more table, external table, which we reference to this file where all the list of files will be as links to the main files. And then there are a question like, what if the main table is changing? How do we allow this table, which we create as a second one, to be also updated as well? So there are two options. Either we set specific property on the table that will allow to update the manifest file anytime the main table is changing, or we just regenerate it explicitly. So we went with the option A here, and it works perfectly fine. This data can be queried by Athena and Redshift without any issues. Okay, so with regards to the use case, let me first remind how the whole pipeline looks like in a nutshell across different pipelines or use cases. So we have product database where we copy data to so-called input data folders. Then we register this data, and when we start to call this data as row tables or row data, and then when we do something useful with this data, we call it aggregated. And these aggregated tables, we also call them derived tables. So one of the use cases to aggregate sales data, and it's called fact sales use case. Technically speaking, it's called this v_fact sales. There are other use cases, different price list comparisons, but what I would like to show you is that complexity of this use case and how we implemented it. Here on the right-hand side, you can see like a tree or graph, which shows the path of building the final table based on the root and children nodes. So every blue node here is some SQL view code, and every gray node is a table. So we ingest around 20 plus tables, and in order to aggregate this fact sales view, we first run around 7 or 8 intermediate queries in a specific order, and then we have a master query on the top, which a query several screens long that builds a final flat table like a data mart with 100 columns. So this is the complexity of this use case. And from the data engineering perspective or our team perspective, this is the where our story ends. So we just build this table. We also create some SQL view on top to manage those custom expressions for the table through the API, and that's it. That's end of our story or use case. Then the other BI teams are using this data and then add some change requests to this shape of the table. So technically speaking, how we build this final table, we maintain a set of files per each use case with this SQL extension, and every file contains Spark SQL code. Then we also came up with another JSON configuration which describes the graph of the queries to be run in specific order. Every query here on this right-hand side also has some properties like what to do with a specific query. But in a nutshell, it allows us to run all these files here on the left-hand side in specific order, and order will be corresponding to this graph. So it will be collapsed from the child nodes to eventually to the root node. Yeah, and also it's worth to say that sibling queries, which are on the same level, will be running concurrently. So we'll build some small library for Spark that just traversing the files, SQL files per use case, and run them either concurrently or in specific order that guarantees that final SQL query that produces some data frame will succeed. Eventually, we have as the output some table, which we call derived table. It may be quite wide, right? So this particular use case have more than 100 columns. And this table can be built on specific schedule and have some metadata, some tags on top of this derived table. Yeah, we didn't really come up with a proper definition of the data product, but it will be refined. And this is the whole question of the data governance topic, which will be addressed in future. So for us, the data product here is just a table which we expose with specific interface to our data consumers. All right, so we're almost at the end, and the next topic is about continuous integration and deployment. While building whole pipelines, the API layer and Airflow code, we came up with some Git repository, which we call datalake core, where it contains almost everything. So we may say it's kind of monorepo that producing some artifacts as binaries or the packages to internal JFrog Artifactory system. And then we have different product teams which also started to have own kind of data sub-teams, which we train and show how to use the code for them. So eventually, it's not really something like a data mesh that you may heard of, organizational structure, but it has some traits from this organization structure. So every product team then consumes our code through Artifactory as a binary dependency, and they also can build their own Spark jobs and then create a workflow pipeline and schedule on our infrastructure. From CI/CD perspective, that's a schema that used implemented by our team, but it's quite the same for other teams. So for continuous integration, whenever the data engineer changing something in Git, so in our case that's Gerrit, it's every change to a specific branch triggers the Jenkins job that compiles the code, runs some tests, and that's it. So this is one flow with this left-hand side flow, right? It's a change, right? It's this color. And another one is this, like a light green color, is about to release a new version to the Artifactory. So that the command called git tag. So once the engineer tags the specific git state, it triggers another Jenkins job, and then we have new artifacts in JFrog Artifactory. That's could be a new version, good to be deployed, and there is some agreement or somebody would be notified that we're now ready to release new version. And usually it's the DevOps engineer within our team who is doing the next step of deployment. And so how this flow look like is, again, it all starts from the Git perspective, and we have another repository here which contains all the Terraform scripts. So that core monorepo doesn't contain Terraform scripts. These Terraform scripts are in another repository, and Terraform scripts here representing the whole deployment of everything what we have, as well as the new version of some core code or pipelines and other things. So first, the ops engineer was asked to deploy a new version. He or she was notified with a new number, with a new version number. So they changed this. They use this number in some specific file. They commit this file to Git, and then they trigger the Jenkins job. Jenkins job identifies the new commit in Git, and it starts to run the deployment job. Since this new Git commit, where ideally the last Git commit contains this new version of the system that needs to be deployed. In the same time, or right, it starts. Once it started, it pulls the new artifacts from Artifactory. This is how we link everything to the release flows before, right? And then end step of this Jenkins job, so all it's doing within one job, it's applying new resources and new artifacts to the Amazon environment. So there is, as I said, 3 different accounts and 3 regions per each account. Okay, and one more slide about tenant onboarding procedure. You probably recalled I mentioned at the very beginning that we have processes like tenant onboarding and tenant offboarding, where we first add some kind of customer to the data lake. It also has own Jenkins job. So first of all, some product manager has to come to us, say that we need to onboard this tenant C, and usually a DevOps person running specific Jenkins job with input parameter, and this Jenkins job creates almost everything. So it creates specific users for source database, creates additional credentials in the secret manager in Amazon. It also runs Terraform scripts to configure the common resources, to configure the tenant resources. And in maybe 30 minutes, you already have completely deployed tenant and specific region. And the last topic for today is about data lake improvements. So we were developing the whole platform, I think, during the 1.5 years. And of course, there was some priorities, and some things were with high priorities related to the business use cases milestones, but some things like optimizations and engineering things were on a lower priority, but we're taking the optimization, of course, time by time. And what we found that some optimizations also make sense on top of this architecture are mainly related to operations and the cost optimization. So we don't want to spend much more time sitting and monitoring this pipeline. So the idea is to automate the tenant onboarding and offboarding procedure completely. So the new tenant needs to be enabled very quickly into the system. The monitoring itself needs to be improved, although we have Airflow UI there, right, and different Amazon UI services, but it's not enough. So it should be some kind of ops dashboard, perhaps developed specifically for this project. So we need to optimize some input formats to go from CSV to Parquet at least. The whole data cataloging area also requires some improvements. So today, offering from Amazon Glue Catalog is quite, I would say, poor option. So on the market, especially on the open source market, you have much more structured solutions for data cataloging that you might deploy as your own deployment in Kubernetes. Also, from cost optimization perspective, so most of the heavy lifting jobs or pipelines, which are constantly running time by time, Spark jobs. So we found that using only Glue ETL might be quite expensive option over the time. Also, shared service like Redshift, perhaps one of the expensive services today for data space on Amazon. And the reason why we use it is that our BI tool of choice is working fine with Redshift, but not working fine maybe with Athena or something else. So that's also a bit of issue with that. And the idea is to try to find some maybe another BI compatible tool, or maybe some connector in the middle, so which would simulate the Redshift or something like that. That would allow us to get rid of Redshift completely from the picture. That would also reduce the cost significantly. That's the main improvement. So I think that's it from my side, and thank you for your audience.
Yeah, thank you, Alexey, for your presentation. Fortunately, I can see you. Yeah, I have it's too dark in your room. Yeah, so
okay, let me try. Make it a bit
okay.
lighter.
Yeah, I have very interesting presentation. I have enough questions with you to discuss. So first, you mentioned about Airflow and that is shared between tenants. So how have you actually split the access between tenants for separate DACs? Because as far as I know, so dashboard is single. So do you mean that all tenants have access to all DACs?
Mm-hmm. Yeah, it's still we can see all the DACs from all tenants at one Airflow cluster. Actually, we didn't need to split the view or access because the only data team is working with Airflow. There is no customer who is working with the Airflow on its own. That is why we could afford ourselves to just to not isolate that within one cluster. Otherwise, we would have to deploy a cluster per tenant, or maybe even think about different solution than Airflow itself.
Mm-hmm. Yeah. Also, also, could you please share more details about these tenants? So you mentioned that each tenant has same resources. So do you mean that they all have same version of platform? So did you have to manage different versions in separate tenants?
Yes, good question. So maybe let me just come back to the slide of this resources separation. So actually, there's 3 layers where every region gets common resources and the tenant resources. The count resources are something that is very small, and mainly because of some services require some IAM policies which cannot be copied from one region to another region within one account. So let's remove the account resources from the picture. What is left is common resources and tenant resources. The common resources are we call them also system resources. Those are like APIs which are not tenant-based, like those lambdas, or some system buckets in S3, our code itself, shared clusters like Airflow and Redshift, and many other things, mainly configuration to IAM, which makes sense to deploy for everybody within one region. And now coming to the last layer, the tenant resources like again, IAM policies, specific S3 bucket for this tenant only, and some different configuration for this tenant only. Yeah, and the versions, how do we maintain versions? So I'm not sure if you work with the Terraform in general, but whenever we change something for common resources or tenant resources, we rely completely on this tool in Terraform, which is the infrastructure as a code tool. And if it detects some changes that, for example, tenant bucket has changed its properties to now have some specific access, it just identifies this upgrade automatically, so that we don't really need to upgrade some resources to specific versions, happening automatically, again, thanks to Terraform.
You mean that you didn't have to manage different versions of this tenant resource, so
Right.
for different tenants?
Right. We didn't have to do this, and also, so we have this. The common resources at the system level. And we upgrade the whole system for all tenants at once, so we don't need to have different things for different tenants. However, if we really need some kind of different behavior for some tenants, or something like that, then there's only single place where it's actually was requested. It's on the level of workflows, on the level of the business code. Those derived tables. For some tenants may have different requirements, or they sit on all the schemas of the product, of the data that we take in as a source. There we just come up with different code in different folders, and that corresponds to some version that is coming not from us but from the source system. This is the only single place where we may have to have different versions, but that again, not those changes are not like among the tenants, they are more among the version of the of a specific product. So our system depends on the data that is coming to us, and that was the requirement. But eventually, we've come up with a quite generic system, and you've seen during the slides I showed a couple of JSON files where they're used as a configuration, and eventually, yes, you can say this tenant has to use this version of the business code, and so it's a lot of configuration parameters where you can override behavior of different tenants within a region and within account.
Yeah. Also have a question. So what problems did you have, or maybe you solved during creating multi-region platform? So, for example, I don't know, I noticed that you have maybe single, multiple JFrog. Maybe you have some problems with accessibility between multiple regions. Oh, by the way, why did you have to create multi-region platform? Is it due to resilience, or so what's the reason?
Yeah, I got the question. Yeah, it's really an interesting question, because actually, if we could, we wouldn't create this multi-region or multi-region deployment system, because it's lots of work. It's also lots of operations, even though the deployments are very similar. So, but the reason is because of the business. So this company for whom we build the data lake, operating, as I said, in these 3 regions: North America, Europe, and Asia. And they are contractually obliged to keep the data in those regions where the customer actually based on. So, for example, if we deploy, if they sold a product for a customer from Europe, eventually this customer can also be upsold to have a data lake service. Their data also needs to be in the European region as well. So we cannot, for example, deploy everything, all the computer sources in US East 1 in North America, and serve those infrastructure for European and Asian customers. So that's the requirements, and that's the same for all the regions. So if we deploy somebody from Asian region, they also has to be there. And it all starts from the OLTP database. So those primary products, so applications, which we're talking about them today, they are also region-based. For example, this company, they install or deploy some client in Asia. They also enable their application, their deployment in Asia. And then we add our add-ons of data lake there to this region. So that is why we have to support all this bigger enterprise architecture here in the smaller kind of footprint of our data lake. So our data lake, as I mentioned, is just the one piece. It's important piece, but the whole SaaS platform that they have is much bigger, so it has more other applications.
Okay, yeah. Also wanted to ask you to share maybe some experience when AWS services wasn't stable enough. Maybe you just faced with some problem with AWS service. For example, personally, me had issues with DMS. Yeah, it wasn't stable, and it wasn't quite informative. Yeah, so maybe something from your experience.
Yes, I agree about the DMS. So it was confirmed by multiple teams during the project implementation. That's perhaps one of them. I just opened the diagram about main flow to show what we've used there. All other services quite simple and stable with regards to usage or issues. We don't really have any problems. With regards to DMS, it's a not fully serverless service. It has some EC2 instances that you need to choose to run the ingestion task. But when it's running, it's kind of invisible. But in order to first time make sure it's running smoothly for your database, for volumes that you have, you may have some different errors out of the DMS, saying some errors, they are not really readable. And we have to have several request tickets to Amazon support, where they really told us what to do, what to change in our configuration to avoid those errors. So that was, yeah, lots of time spent there. But eventually we've made it work, and it works fine eventually. And we know where we shouldn't perhaps use it for future, and what to avoid. So we kind of learned also how to use it. Other services, perhaps GlueTL, you might know it's a serverless service, which you just submit a job and you specify how many workers you want to have. I would say if I compare GlueTL versus just EMR Spark jobs, GlueTL a bit harder to debug, because you have all what you have is this CloudWatch logs, and you need to read them in a bit inconvenient way. Most of the issues are first time related to IAM policies, that something cannot be read by a GlueTL job. Then, so it's a bit much longer to make it work first time than just EMR job. Also, login is a bit different than in EMR Spark jobs. That perhaps another one that added a bit of headache, but that's much lighter than DMS was.
Yeah, got it. Also have a question regarding this data lake and data tables and Hoodie. As they support each other, so can I just switch between, for example, between data lake and Hoodie, so or I need to reload everything?
Well, yeah, so let me maybe just open one comparison table there. So actually, they are not really depend each other, but you can migrate from one to another. I don't remember exactly about the Hoodie, but both technologies, they have manuals how to quickly start with them. So usually people come into Hoodie or Delta Lake or Apache Iceberg, or maybe some additional new libraries pop up this year. I'm not sure. They're very fast to grow in the space. You start from some kind of Parquet data, maybe CSV data or so, and there are some receipts how to change your data format into the Delta Lake or a Hoodie. And same from kind of migrating out of it. Similar manuals exist for all of them. So if you'll end up using Delta Lake for some time and you don't want to use it anymore by some reason, you just export this data into the Parquet, or even just use an additional code into your Spark job to just read this data as a Parquet, not as a Delta Lake. And so I must say that migrating to and out of it is quite easy. So you just would need perhaps to run one-time job to migrate all this data. And some of these technologies like Hoodie or so, they provide even kind of automatic upgrade. So you just run some job that it will discover again, okay, this folder is not Hoodie-like table, it will register as a Hoodie table. So all of this technology, they are coming with design how to allow users or data engineers to easily onboard onto these technologies.
Yeah, okay. Yeah, thank you. Thank you very much, Alexey, for your presentation.
You're welcome.
It was really interesting. Yeah.
Thank you, Alex.